All right, so we're continuing on with our notes, and I just wanted to mention something. Um, Once I finished these notes, I actually added some programming notes. In particular, I wanted to be sure we understood how to do this, find orthonormal columns in MATLAB or Octave. Also, I went ahead and took a look at the commands in both Python and R. So whatever your flavor of programming languages, you can do that. So we showed how to get an arbitrary orthonormal matrix. And then we show how to, or one of the exercises, new exercises, asks you to do this and compute the projection of x onto the subspace spanned by the first, I think I said first four columns of Q. I called it the matrix Q that has the orthonormal columns. Okay, so give those a try. The other problems in the homework are things that you're going to do by hand, but I think it's important to be able to see how to do this using the computer as well. Good, so those were exercises. The exercises actually changed from page 41 now because of the addition of the programming notes. So I'm going to update the class website tonight once I finish with these videos. Okay, good. All right. So continuing on now into the notes, we're looking at section 4.2, which is the four fundamental subspaces associated with a matrix. And so if we have A, which is m by n, with rank k, right, then the four subspaces that are associated with that matrix, you can draw as these lines here represent subspaces, and so it looks like a coordinate system, but this is actually, for example, this axis right here corresponds to the row space of A, and this axis right here corresponds to the null space of A. And so if A is m by n, this is Rn, right? And then this would be Rm. And so our mapping, right, takes x and goes to A times x. So if A is m by n, then x is a vector in Rn, and A times x is a vector in Rm. Good. So this will be the column space of A, and then this is the null space of A transpose. Okay, we don't do very much with the null space of A transpose. It's there just really to fill things up. Okay. Now, do you remember what these are? Actually, it's pretty straightforward. For the row space and the column space, the row space is the set of all linear combinations of the rows of A. The column space, what would you suppose that is? It is the set or the space of all linear combinations of the columns of A. Okay, all linear combinations of the columns of A. So row space again, that was the linear combinations of all the rows of A, and the column space is all linear combinations of the columns of A. Good. All right, the null space of A is the only one that we probably make sure we write down. The null space of A is the set of x such that A times x equals the zero vector. Okay, so it's all the vectors in Rn that get mapped to the zero vector in Rm. Good. And so we know how to solve for that. Excellent. So those are the four subspaces. Um, the nice thing about this picture is it actually relates how the subspaces relate to each other. And so, for example, this suggests that these spaces are orthogonal to each other, and in fact they are. Oh, I should say we should probably talk about this rank. Do you remember what the rank of the matrix is? The rank of the matrix is the dimension of the column space, and so automatically we get that the dimension of the column space of A is K. And so if this is Rn, then the dimension of the null space of A transpose would have to be M minus K. Good. Now, the dimension of the column space is the number of pivots in your reduced matrix, right? The RREF of your matrix A. And so, does the number of pivot columns equal the number of pivot rows? Yes, number of pivot columns is equal to the number of pivot rows because the number of pivots don't change. And so the dimension of the row space is also equal to K. Okay, and so therefore the dimension of the null space of A must be n minus K. Good. And so we know now what the dimension of all four subspaces is. Good. Now, how would you know, what about the four fundamental subspaces tells you, what tells you that a matrix A is invertible? Do we know something when would the matrix A be invertible? Well, the idea here is that, well, there's a couple things. I guess that's kind of a trick question, right? Because we have an m by n matrix here. Our matrix is going to be invertible. First of all, our matrix has to be square, right? So m is equal to n for A to be invertible. And then if that's true, you need the matrix mapping to be onto Rn, which means that the entire space is spanned by the column space of A. So the column space of A takes up all of our n in that case. And so that means that the dimension is n, which means that the dimension of the row space is n, which means that what's the dimension of the null space of A? 0. Right, the null space only contains the 0 matrix. Good. So that's just a quick example of how the four subspaces kind of help you determine what's going on. Good. All right. So let's prove one of these things. How about the null space of A is orthogonal to the row space of A. So we'll prove that the null space of A is orthogonal to the row space of A. Good. All right. So what I want to do then is I'm going to take or let x be an arbitrary vector in the null space of A. And then what will I show? If y is an arbitrary, or, well, let's put it another way. What I want to do is I want to show that x is orthogonal to the row space of A. So one way to do that is I can show that x dot any row of A is equal to 0. Good. And so let's see if we can show that. Well, here's a hint. If I just take the matrix A times the vector x, now I know that my x is in the null space of A, therefore I know that A times x must be 0. And so I can rewrite that in terms of the rows of the matrix A. And so I could rewrite this as A1 is the first row of A, A2 is the second row of A, and so on down to A sub m is the nth row of A times x. and I know that that must be 0. And so what happens when you take this product now? Yeah, this is just shorthand for saying that the row, well, I should probably put a vector over the top of that. These are row vectors, right? That's what these little lines are for. This is a row vector times x is equal to 0, or that means that the dot product of the first row with x is equal to 0. And similarly, the second row of x dot x must be 0, and so the nth row of x a dotted with x must also be 0. So therefore, x is orthogonal to all rows of A, right? So therefore, x is orthogonal to the row space. Good. So that was true for an arbitrary vector in the null space. Therefore, the null space must be orthogonal to the row space. Good. Okay, so I paused for a second to write down a problem here. I'm given a matrix A, and I've written down the row-reduced echelon form of A. And the idea is I'd like to find a basis for the column space of A, the row space of A, and the null space of A. And so how am I going to do that? Well, from the row-reduced echelon form of A, I'm noticing that I have two pivots, right? And so therefore, I know that the dimension of the column space is equal to 2, and so is the dimension of the row space, right? So in fact, let's go ahead and start with the column space of A. So the column space is two-dimensional, right? And so that's going to be the span of now the vectors, two column vectors. These are going to be two vectors in R3, right? And so I don't want to use these columns, right? Because I've done row reduction on those. I want to use the original columns from the matrix. And so that's going to be 2, minus 2, and 3, 0, 5. That was a minus 5 there. Good. Do you see why, by the way? If I took these two columns to be my two basis vectors, I could never have, for example, anything in the third entry there except 0, right? And of course these columns have lots of numbers there. Good. So therefore this is going to be the basis for the column space. Excellent. Okay. Now we need a basis for the row space. I'm going to write these as columns, but they're coming out of the rows. And by the way, what dimension are the rows? Did you say the rows are in R4? So they're going to have 4 entries apiece. And now I look at my matrix and I see I've got these two columns here, or the two rows. Now do I use the rows out of the row reduced echelon form or the original matrix A? Well, remember, to get from the matrix A to the row reduced echelon form, we did row reduction. And actually row reduction is reversible, right? So we'd be able to go backwards from here, from the row reduced form back to the original. That means that you can use the first, or we should use the first two rows of the row reduced echelon form for the basis. Good. And so then the last thing is going to be the null space of A. And so for the null space of A, we want to actually solve this matrix equation. Well, I just realized I'm going way over. Boy, time just flew by. It's already 14 minutes. So we're solving this system of equations. In fact, let me just write it as a matrix this way, because we just have the zeros on the end, right? And so I'm going to pause this here, and we'll finish this off real quick in the next video and continue from there.